It's my pleasure. I'm very excited to introduce on the first day of the courses our speaker of today. Liz already gave like a beautiful introduction of the speaker, so I'm just gonna thanks Monica for being here, and the screen is yours.
Hi everybody, welcome. Let's see, I am still waking up. So definitely interrupt if you have questions and stuff, or put them in the chat, and Christina will help alert me to them, or Laura will. And let's see, I'll do my best to answer them. I'll do better when my brain is fully awake. And also, so let's see, I'm talking this week about the Symmetry Group and representation theory and related combinatorics, and we might talk about some groups and algebras related to the symmetric group, not exactly, using a lot of diagrammatics. And I think the course is going to evolve over the week, depending also on what your interests are. All right, so I think a lot of you have familiarity with the symmetric group, and I'm going to start there to be concrete and to set up at least some notation the way that I like to do things. And I should say, so these lecture notes, as was mentioned, will get emailed to you after the fact, but if you want to see what's here, even though not everything is written on it yet, if you go into Sococo in the lecture hall under share, I put them there, hopefully that works. All right, so the symmetric group, SN, now I use like this funky font for my S's just because in my research there's so many letters S everywhere. I kind of have to have a different one for each, but if that gets annoying for people, I'll just move it to plain S anyway. So the symmetric group, right? We've got n factorial permutations of the letters 1 through n, and it's a group because you can compose permutations. And one way to think of it is that this group acts on the set 1 through n. And I'll call this sort of the natural action. So when I use the word natural or possibly defining, this is what I'm referring to. Okay, and I think we had a little bit of review on the weekend about group actions. And so what's our favorite way to write the elements in the symmetric group? Well, one way is it's a permutation, right? So if I have 1, 2, 3, 4, 5, I'm writing them in some new order, like 5, 2, 1, 3, 4. Okay, but remember, a permutation is a bijection. So I can also think of it as a map. And so this writing out, so what does this mean? This means it is the map where, actually I'm gonna write them underneath to be more like the notation that we use topologically. I have the numbers 1, 2, 3, 4, and 5. And this is saying, you know, this is where I map 1, 2, and this is where I map 2, 2, and so on. And this notation, there's different names for it. Some people call it window notation. Some people call it list notation or one-line notation. I will probably use all of them interchangeably. And so forgive me for that. Okay, but I'll always try to put these brackets around it to denote this is the notation I'm using. All right. And so what's very nice is to draw a picture of this, the fact that I'm telling you where 1, 2, 3, 4, 5 go. Right, so I might write 1, 2, 3, 4, 5. It would be rather boring if I wrote 5, 2, 1, 3, 4 here. So instead I think of this as another copy of my 1, 2, 3, 4, 5, and let's see if I can do this correctly. So if 1 goes to 5, right, 2 goes to 2. Let's see, you're going to have to also do this in the exercises, but let's do this one. So 3 goes to 1, and notice when 3 went to 1, it's really good that I was careful and I didn't, you know, have 3 all meet at a point. It's better to wiggle your lines around so they don't do that. And then, and so on. So we tend to have things flow up in these pictures. Okay. And now, but other notations you might know for the symmetric group are cycle notation. So I said, you know, 1 goes to 5, and then If you check, 5 goes to 4, 4 goes to 3, 3 goes to 1, and 2 goes to itself. And that's how I learned to do the symmetric group when I was in school. And cycle notation has a lot of benefits to it for composing and for conjugating. Really, cycle notation is a great way to go. If you want to draw a picture of cycle notation, you can just have the dots 1 through n, and you could draw arrows. You can just have one copy of each dot and just have arrows running around the page. So many benefits to cycle notation, but it's not unique, right? If I can rewrite this cycle as, I could have said 2 goes to 2, and then 4 goes to 3, goes to 1, goes to 5. That's one drawback. You also don't know what the n is for Sn. You don't know that it's S5 necessarily. This could live inside of S8. But maybe that's actually a benefit, not a drawback, because of course in list notation, you have to then have list 8 numbers. Okay. So it'll be beneficial to be able to go back and forth between these different notations. But one thing that we'll get to practice in the exercises if you choose, if I give you a permutation, writing its inverse in list notation, and in particular its diagram, and to see pictorially what goes on with the diagram when you take the inverse. So if this is something you haven't done yet with the symmetric group, definitely try it in the exercises. Right, so how do we compose permutations? Well, they're bijections, you just compose them. But pictorially, we can do this with vertical stacking, and we saw some of this on the weekend. And so remember that with functions, you write f after g, which means you do g first, and then you do f after, and that can be something confusing. And so you have to remember what direction you're going. All right, so if I want to compose these two permutations, I can just draw their wiring diagrams. And then, but you notice you can straighten this out a bit, right? This guy crosses over here, I could pull it over. And then it becomes slightly more simple. But you don't know maybe until you draw it, until you look at the permutation. Does it become more simple when I wiggle around the wires, or does it actually pick up an extra crossing? And so in the coming lectures, we might talk a little bit about that. So, all right, so keeping on getting the basics of the symmetric group down, we can just list all the permutations in the symmetric group, but it's a group. We like to give them maybe with generators and relations. And that's going to be helpful because when we're looking at categories later, we're going to be talking about generators and relations. So let's get used to it with groups. So some of our favorite generators for the symmetric group are the simple transpositions. I tend to call them SI. So S1, S2, S3 up to Sn minus 1. And SI just swaps I and I plus 1. So in list notation, it would look like 1, 2, 3, 4, 5 up to the n, which would be the identity, except at the ith and I plus first positions, these guys are swapped. And so in my braiding diagram, right, just at my ith and I plus 1 positions, I have this one cross. Okay. So, and I should mention that and we saw on the weekend that sometimes, so I just drew this as a cross, and it's not sort of, it's not really a 3-dimensional picture, it's a 2-dimensional picture. But sometimes you might see a 3-dimensional picture where actually it's an overcrossing or an undercrossing, or what we call a positive or a negative crossing. But we're not doing that for the symmetric group, we don't care. And so that means that if you do a crossing twice, right, you can straighten it out. And so that means we have the relation that SI squared is the identity. And we had a question on the weekend about the braid group. And when you have the braid group, which is a different group from the symmetric group, you don't have this relation. Okay, you really do think of strands as having over or under crossings, and then you just get twisted up and you don't have this relation. But we do have this relation in the symmetric group. Okay, and as we saw with the Hecke algebra, if we have these skein relations, we might have some different relation that this overcrossing satisfies. And so just drawing these pictures isn't enough of these generators. I have to tell you what the relations are. So I call this my quadratic relation. Now there's also a braid relation. So what are the braid relations? And again, we saw these on the weekend. And so even though the quadratic relation tends to change, we almost always are going to have these braid relations, and these are type A braid relations. okay, which is that these transpositions that are far apart, meaning the indices I and k that are far apart, they commute with each other. And ones that are close together, consecutive, like 1 and 2, 2 and 3, 5 and 4, they satisfy this other relation, sk si sk equals si sk si. You might ask, why didn't you use I and j? Everyone uses I and j, because my j's look like that. Okay, so, and then we have a nice picture that goes with that, right, you can think about why that's true, all right? You can think about it algebraically and write the permutations and compose them, or you can see them on the pictures. And again, we did see this on the weekend as well, that, right? So here's maybe I do an S4, and then after that I do an S1, versus here I do my S1 first, and then I do my S4. And again, if you just kind of put these on equal footing, right, they both just look like this kind of permutation. But you can see that if you wanted to think of this permutation and unravel it and write it in terms of generators, right? So as it's written here, I have written this word. This word is, let's see, so first I did S4 and then I did S1, whereas this word is first I did S1 and then I did S4. And so algebraically, you have to do a little bit of work to notice these two are the same. So that's one of my relations. In list notation, they would give the same permutation. It would be obvious they were the same. Okay. Going backwards though, if I just draw this picture of a permutation, I said write it in the generators, that means you have a choice. You have a choice of writing the generators. And so this picture is a little bit inferior to writing it in generators if I put these crossings on the same level. But I get to do little isotopies to my pictures. And so it's to my benefit to wiggle these X's around so that this cross is definitely above this cross, but definitely below that cross. So that's up to us, but we should wiggle our diagrams a bit to do that. Okay, and then again, we have a picture of this other braid relation, this 3-term braid relation. And if you really draw it out, I find it to the naked eye a little difficult to see these two are the same. But if I draw it as kind of an X with the red line that gets to pass back and forth, it's a little bit more satisfying to see that they're the same. And you'll see that when these are all positive crossings, the same relation holds. If you have the overs and unders in the correct way, the red line can really just pass through the center of the X, right? But if you mix up positive and negative crossings, it might not be able to. Okay, and so on the exercises, you'll have to have a chance to start with the wiring diagram like so, and then write it in terms of generators, if you haven't done that before. And again, it's sensitive to how you draw the picture, right? Which crossings do you choose to put above or below the others? But if you believe these pictures, because there's 1, 2, 3, 4, 5 crossings, you should expect to be able to write this using 5 of these SI generators. Okay. And that's actually called the length of a permutation. So the minimal number of generators that you need to write it is called, its length, right? And if you believe what's going on in this picture, you're really just counting the number of crossings here. Okay, but the number of crossings, when it's minimal, when you straighten things out. So to scroll back up for a second. Right, in this picture here, whoops. Oh. Right, this is one way to write the identity as 2 guys crossings. And you might say this guy has length 2 because I see 2 crossings. But it's not minimally so. You want to wiggle around your strands to the least number of crossings, and that's really the true length, would be 0 here. Okay, so the identity has length 0. All right, and so this is also equal to the number of inversions of your permutation, which is something you might ask, well, if I have to always draw the picture to read the number of crossings to draw my picture well, that might be quite a difficult thing to do. Well, there's another way to see this. This is the number of pairs, I less than j, such that when you do, well, let's say sigma is your permutation, that sigma of I is greater than sigma of j. Okay, so that's an algebraic way that you can compute this number and know how many generators to expect. But again, it's not unique. You have to do some work to write an actual expression. And there's an exercise to give you a permutation. And you have to write all the possible, these are called reduced expressions of them, all the ways to write them in generators using always say, only 5 SIs. Okay, so that's getting us down with some of the vocabulary and notation in the symmetric group, which might have been familiar so far to everybody. Okay, so let's talk about restriction. We want to get to some of these functors that we have. Well, let's just start with, we said the natural action, S5 acts on the set 1, 2, 3, 4, 5. And you might recall that's the same thing as saying I have a homomorphism from S5 to the permutations of the numbers 1, 2, 3, 4, 5, which of course the permutations of 1, 2, 3, 4, 5, right? That just is S5, basically by definition. Okay, and the homomorphism here actually is the identity homomorphism in this case. At least if I order 1, 2, 3, 4, 5 as 1, 2, 3, 4, 5. Okay, so given such an action, and you give me any subgroup, H of G, you can restrict that action. And some of my favorite subgroups are these subgroups that, whoops, that wasn't supposed to be there. Well, I'll leave it there. A Young subgroup or parabolic subgroup. So something of the form, take those permutations that are allowed to swap 1 and 2, and those that are allowed to swap around the 3, 4, and 5. But you're not allowed to swap like 2 and 4. You only get to swap within the set and swap within the set. And so as a shorthand, I write that as S2 cross S3. It's not technically equal to that, it's just isomorphic. Because if you think S3, you would start over again with 1, 2, 3. Well, don't use 1, 2, 3, use 3, 4, 5. Okay. And so these are called Young subgroups or parabolic subgroups, and they'll turn up a lot. They're some of the nicest subgroups of the symmetric group. Okay. And so one way to think of it is, right, I have this set, 1, 2, 3, 4, 5, and I decided to cut the set into disjoint parts, 1, 2, and 3, 4, 5. And then I'm just restricting the action respecting that cut. And it might be useful to instead of writing this S2 cross 3, I can write it as S of the composition 2, 3. All right. And so, yeah, if you restrict this homomorphism to the subgroup, right, I'm restricting the action. That's what we do when we do restriction. So restriction tends to be very natural. It's throwing away information. If G knows how to act, then any subgroup of G knows how to act. And diagrammatically, what's going on? What's going on with how to think about the subgroup? Well, in the same way as we cut 1, 2, 3, 4, 5, we can take our wiring diagram and imagine that there's a cut between the 1, 2, and the 3, 4, 5. And so, for instance, here's the identity permutation, but I imagine that there's this line there that's stopping any of the blue lines from crossing it. It's like this big solid wall. And so, again, you're allowed to permute around in the 1, 2 land and the 3, 4, 5 land, but you're not allowed to cross this big line. Maybe I should have made it like thick and red and ominous looking so that you can't cross it. All right, so yeah, and so of the different subgroups you can have of the symmetric group, these parabolic subgroups or Young subgroups are the ones that we tend to see the most often and like to use. We can take conjugates of them, but there's something really wonderful about these. And again, I can have general notation. I can have like an S beta, where beta is any, I call it a composition event, just a tuple of non-negative integers that add up to n. Okay. And let's see. Okay, so, right, that's groups acting on sets, but we might want to act on vector spaces, actually, so that we can linearize what we've just done. okay, and then start living in that land. So what do I mean by linearize? Okay, so first of all, I need to pick a field. And for this week, I'm pretty much having my underlying field be the complex numbers, just to make things easy, because it's characteristic 0 and algebraically closed. It turns out if you're talking about the symmetric group, the rational numbers gets us where we need to go. All of the theorems that we say over the complexes would work just as well over the rationals. But let's not bother with that because we're not really worrying about number theoretic concerns. On the other hand, if we're talking about the Hecke algebra and we have a parameter Q floating around, maybe we want our field to be C adjoin Q, or the fraction field of C adjoin Q. Or, you might want it to be some other field with other parameters in it. You might want to have not a field, but a polynomial ring. So, but in the symmetric group, I'm just working over the complexes. Now, you might say, what about characteristic P, non-zero characteristic? That's super interesting. And we saw in some of the 3-minute talks yesterday, which were absolutely excellent. I thought they were amazing. That a lot of people are interested in characteristic P symmetric group, not even just characteristic P representation theory, but even characteristic P symmetric group has a lot of open problems in it, really hard open problems, because they've been around for more than 100 years. And that is really relevant to what's been going on at IAS all year long. Okay, but I don't think I'm going to end up talking about it this week, unless if there's a lot of interest in it, we can definitely flow in that direction. Okay, so how am I introducing this field, the complex numbers, into the fray? Well, right, so far we have the group, symmetric group acting on the set X, which I took to be, say, 1, 2, 3, 4, 5, but it could be acting on any set. And so to linearize, right, I passed from the group to the group algebra. And I pass from a set to a vector space. And how do I do that, right? How do I do that? I just make the elements of the underlying set correspond to a basis of the vector space. And so that means in the group algebra, these n factorial permutations now become a basis of this as a vector space. So this is an n factorial dimensional vector space, but it also has a multiplication on it. And the way that you multiply is you just use the distributive law, because you know how to multiply, or you know how to compose permutations. And so you just take a linear combination of permutations, and how you write your notation really matters, so that people know what your linear combination is looking like. How do you compose two linear combinations? You use the distributive law. And then you know how to compose the permutations, and you just multiply the coefficients. And one benefit, well, there's many benefits to passing to this linearizing. We'll see some of them in a minute. But one benefit is we have this relation in the symmetric group that if you do the transposition SI twice, you get the identity. And we could rewrite that if you want, as saying SI minus 1, we identify the identity in the symmetric group with the coefficient 1, and just the 1 is the identity of this group algebra. We could factor this relation to SI minus identity times SI plus identity equals 0. And again, we saw that on the weekend with the Hecke algebra, our quadratic relation there, we could write it factored in this way. And that's really useful. It tells you about, say, eigenvalues, that when this is acting on a representation, SI can only have eigenvalues plus and minus 1 at most. Its minimal polynomial has to obey this. And so it also shows it's acting semi-simply, which is a nice thing to know, even though since we're over the complex numbers, this kind of thing is going to happen a lot. All right, so let's look a little bit more at this vector space that we get. Right, so in our running example was n equals 5. So I said you make X be your basis, right? So 1, 2, 3, 4, 5 is basically my basis, but let's just call them E1, E2 up to E5, because we tend to use that for the standard basis of what? Of C5, right? So if X has cardinality 5, we're replacing it with a vector space of dimension 5. Okay, now, oh, and sorry, and this is coming up in a second, but we saw this in categorification land on the weekend, right? You had well, you have the number 5, and you have two directions to go. You can think of 5 as the cardinality of this set, but you'd also think of 5 as the dimension of this vector space. So replacing just the number 5 with these more interesting levels is kind of an instance of categorification. And how do you go back down? The dimension of this vector space giving you 5 is decategorifying, or the cardinality of the set being 5 is decategorifying, giving you this number 5. Now, up above, when we talked about restriction, right, we took the set 1, 2, 3, 4, 5, and we decided to make a cut in it, like dividing out the 1, 2 versus the 3, 4, 5, not dividing separately. Okay, so on the set level, right, we're taking 1, 2, 3, or 5 as the disjoint union of these two sets. And what's happening on the vector space level? Well, we know that we could divvy up the basis, or we could say that C5 is isomorphic to C2 plus direct sum, a C3. Okay. And of course, you can decompose C5 as the direct sum of subspaces in many, 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 many different ways. You only have so many ways of chopping up this set. Okay. So there's more going on the vector space level. And so that's one benefit, or maybe one thing that's more confusing about going to vector spaces. Okay, but the thing to notice here, right? When you do disjoint union of sets, the cardinalities add. And the same way, when you do direct sum of vector spaces, the dimensions add. Okay, and of course, when you're just talking about natural numbers, you just add them. All right, and so we can work with, this is happening in the category of sets, this is happening in the category of vector spaces, but this notion of adding, and categorifying the notion of addition just for numbers, okay, with either disjoint union or direct sum. All right, so yeah, so what are some of the benefits of linearizing? Well, I love linear algebra. I love being able to write matrices and do things with them. I often do them by hand, but you know, if you're good with computers, you can just program them in and be lazy about multiplying them by hand if they're big, or maybe I should say smart. So one great benefit is you get to do linear algebra, which is really wonderful. But another benefit is you can do new things that you couldn't do before. So one thing we could do, well, we have G acting on the set X, we turned X into a vector space. We can take what I can call sort of the orbit sum now of, I'm going to call it bold 1. So we could take the sum over all I in my set X of these basis vectors EI, right? And now when we do that, so that's a linear combination that we weren't allowed to do before with just set elements. This vector is now, I'm calling it a fixed vector or a trivial vector. Okay, and so why do I do that? So let sigma, a permutation, let's go back to X is 1, 2, 3, 4, 5. And let's say sigma like swaps 1 and 2. And then how is it acting? Oh, you know, I forgot to say, right? I said that that the group acted on X, and from that, we should have the group acting on the vector space. Let me scroll up a bit, remind you, right? So how should sigma act on an EI? Well, sigma knows how to act on I, so send it to the new basis vector, right? And so of course, when you do this, that means the matrix of sigma is going to be a permutation matrix. So if you do it in this basis. Okay, so if I'm swapping 1 and 2, that means I swap E1 and E2. But when I go and I take the sum, because addition is commutative, okay, it was E1 plus E2 plus E3 plus E4 plus E5, but now it's E2 plus E1 plus E3 plus E4, E5. Well, there's no difference. You get the same vector back. And so this is a fixed vector. In other words, when sigma acts on this vector, bold 1, you get that 1. And that's why I'm saying it's fixed. Or it's trivial, because it's the trivial action. Okay, and that's true for all of your permutations. And you know, that's a feature you don't necessarily write in X. When you're acting on X, it's not like there's a fixed point, but you do get a fixed vector. Okay, so it tells you a little bit more about what's going on with this set. All right. Yeah. So in other words, X doesn't have any proper S5 invariant subsets, right? There's no fixed points, but it does act transitively on X. You can get from 1, 2, 3, 4, 5 to any of those other numbers by permuting. Okay, but the vector space that we make out of X, V, C adjoin X, it does have proper S5 invariant subspaces. And really, since I'm linearizing, I can think about S5 acting on V, but I could also think about the group algebra, C bracket S5 acting on V. Okay, and we do have invariant subspaces. Okay, and there's an exercise on that. Okay, so you can actually check the nuts and bolts of that, see and find the complement. Sorry, I jumped ahead of myself. You can see, you can check that this is invariant subspace. Okay, so when you have an invariant subspace like this, invariant for the action of your group or your group algebra, then we'll say that our V is reducible. Okay, or meaning it's not irreducible. So reducible, irreducible, mutually exclusive. Okay, and sometimes we'll see the word simple. Sometimes instead of irreducible, you'll see simple. So V is not simple as a representation of S5 or as a representation of the group algebra, CS5. But more than not being simple or not being reducible, it's also not indecomposable. So therefore it is decomposable, right? Either decomposable or indecomposable. It's actually decomposable. And what's the difference between reducible versus decomposable? It's one implies the other, right? If you're decomposable, you would better be reducible, but you don't necessarily have to have the other direction, except that we're working over the complex numbers and the symmetric group where we do. But that situation does not have to always happen. We'll come across this week situations where you can be indecomposable and yet not be simple. That you can be reducible. And so how do we see that it's decomposable? And by decomposable, what do I mean by decomposable? I mean that I have a direct sum decomposition, okay? That respects the SN action. Okay, so to check simplicity or not, you just have to find an invariant subspace. But to say that you're decomposable, you have to write it as a direct sum of not just your invariant subspace, you have to find a complement to it. And so how and why can we find a complement? Why should it be there? Okay. Well, in the case of the symmetric group, I'm working with, say, S5, and let's even work with our natural V. So Cn, or again, this is what I was calling, which I was getting from the action of Sn on 1 through n. Okay, so how do I build a complement if I want to do it, if I know I'm decomposable? Well, one nice thing is about vector spaces, we have inner products. And so we have dot product on vector on Cn, right? We grew up with dot product in linear algebra. And it turns out that dot product is, I'll call it Sn equivariant, okay? Or in other words, Sn preserves your dot product. So what do I mean by that? I'm gonna write dot product not with a dot. You might see B dot W. I'm gonna actually write it as a pairing with angle brackets, because later on we might replace it with other inner products or other pairing. Okay, and so if I pair V and W, that's the same thing if I pair sigma V with sigma W. And this works for all sigma and Sn. So this is what I mean by preserving dot product. Okay, and of course, where have you seen this more largely? In the orthogonal group, right? An orthogonal transformation is one that preserves dot product, preserving length, preserving distances, preserving angles, okay? And if you don't believe me, you can check. So say I take the dot product of these two vectors, 1, 2, 3, 4, 5 with say 0, 1, 0, minus 1, 0. So what do we get? We'll get 2 minus 4, which is whatever it is. But now let a 5 cycle act on both of these vectors at once, right? So instead of 1, 2, 3, 4, 5, it's 5, 1, 2, 3, 4. And then I also brought the 0 up to the top, and here it is. And if you dot product, you're still getting 2 minus 4. All right, so if you didn't believe me, this shows this is a good reality check, okay, that you preserve dot product. All right, and so why make a big deal about preserving dot product? Oh, sorry, before I do that, well, okay, let me tell you, why do I make a big deal? It's gonna let me find a complement. Okay. But another thing that we might want to do is instead of writing this v dot w is the same as sigma v dot sigma w, that means that I could also rewrite it is that v paired with sigma w is actually the same as sigma inverse v paired with w. It's the same exact information as the statement above. But when you write it this way, and you think about linear algebra in general, where have you seen this before? That you have a pairing and you have an operator on one side, and you're saying, oh, it's equal to the pairing where there's a different operator jumped over on the other side. Well, that's what we mean by the adjoint, right? So with respect to a pairing, an adjoint operator is one that satisfies, the adjoint to the sigma would be whatever you can put here to make the statement always true for all v and w, right? So just remember adjoint from linear algebra, because we're going to see adjoints for functors later. And so we can say the adjoint to sigma is sigma inverse with respect to dot product. Okay. So as I mentioned, so we have our invariant vector, our trivial vector, our fixed vector, bold one. And because dot product is SN invariant, if you take the orthogonal complement, so this little perp here is orthogonal complement. If we take the orthogonal complement of that vector and call it W, orthogonal complement to the whole line it spans, that is going to also be SN invariant. Okay. Sorry, I'm just making sure that I'm not forgetting to say things. And actually, you know what? Let me make it, right? It's invariant for the whole algebra, not just the group. Okay. And then in the exercises, you can have an opportunity to check that. And you can think about, you can explicitly describe the orthogonal complement to this vector as these other vectors. And you can look at that space and you can just check for that space. Why should that space be invariant under this action? Okay. All right. And an observation to make with respect to restriction. And as a shorthand, since I'm always restricting to these parabolic subgroups, and it gets annoying to write the S's, I might just write the 5 and I might put my composition beta here. So I might call it restriction from 5 to 2, 3. Because I could decompose my V, which was again, it was my permutation representation, because I could decompose it as this fixed vector and this orthogonal complement, that still holds when I restrict to S2 cross S3. That restriction is going to decompose as you can do the restriction to the first piece and the restriction to the second piece, and I still get this direct sum here. Okay, and part of why that works is because restriction is what we call an exact functor. In other words, if I have an invariant subspace and it's invariant for all of S5, how could it not also be invariant for a subgroup? If all of S5 keeps it fixed, so does S2 cross S3. So invariant subspaces are still invariant subspaces, even if you restrict the group or the algebra that's acting. And therefore, a direct sum decomposition also gets preserved. All right. So having linearized, we already mentioned what happens when we linearize with respect to disjoint union, right? Cardinalities add. For disjoint union, right? If we look at these vector spaces, what do we get? Right? So this is going to be isomorphic to the direct sum of these two vector spaces, right? This is like our C2 direct sum C3, and the dimensions add. Okay, so on the set level, we can do that. Now that's for addition. What about multiplication? Okay, so what about multiplication? Well, what operation do we do that will multiply cardinalities of sets? Cartesian product, right? So if I have X has size 2 and Y has size 3, and I take X cross Y, now I have something of size 6, not of size 5. Okay, so Cartesian product is on the set level if we want to categorify multiplication. Well, what do we do on the vector space level? How are we categorifying multiplication? What can we do that will multiply the dimensions? Well, for these particular vector spaces, right, if what happened with the sets was you take the Cartesian product, that means we want, you can just say, okay, we'll just linearize the Cartesian product. But if we want to work with vector spaces that don't just come from give me your favorite basis and linearize it, we want to have some kind of other vector space operation, and that's a tensor product. Okay? And that will make the dimensions multiply. And so it seems that based on a poll that a lot of people were familiar with tensor product, but there's an exercise on it, which actually it's for the TAs, you guys don't have it yet. I wrote it last night, so I'll export that somewhere and make it available to everyone to practice tensor product and what goes on with tensor product. But what the takeaway of it, you can stick together two vector spaces in a way that makes their dimensions add. Actually, I think I'm going to go into it in a little bit more detail on this slide. We'll see what happens. Okay. Okay, also, so that's, right, so going back to the setting of acting, right, so if G acts on a set X, and maybe K, some totally different group, acts on some totally different set Y. Oh, and this notation, I don't know if this notation has come up yet this week, but instead of, at some point in my life, I started seeing this, instead of writing G acts on, or like, you know, X is a module for G or something, you get this little like circular arrow guy for a shorthand for G acts on X. So if you see this little symbol, that's what you usually mean by it. So if G, some group acts on some set X, and K, some totally different group maybe, acts on some set Y, then G cross K, the Cartesian product of groups, acts on the Cartesian product of the sets X and Y, right? And how does it work? If you have a pair GK and you want to act on a pair XY, well, G knows how to act on X and K knows how to act on Y, and boom, you get a new pair. And so on the vector space level, tensor product level, we can do the same thing. So if we have the group algebra of G acting on the vector space we make out of X, and the same thing for K and Y, then, well, since G cross K acts on X cross Y, that means this new group algebra acts on this new vector space. But again, there's a way to see this vector space as the tensor product of these smaller vector spaces. And again, we can generalize this to not just vector spaces that arise from sets, not just permutation representations, but any representation. And just to warn you about my notation, when I glue together two vector spaces that came from two different actions, I often, instead of just using a round tensor product, I tend to use the square tensor product. It's kind of an outer tensor for me. So if you're wondering, what are these square tensors versus these round tensors floating around? This is my notation and where it comes up. And if you forget, you just ask someone in the problem sessions and so on. Okay. And so, yeah, so you'll have an exercise to remind yourself more generally, if I have two vector spaces V and W, what is V tensor W and how do I think about it? Okay. And one thing I can't, let me just scroll down and see, because I can't remember if I know. Let me put here. So in particular, let me remind you that if I have a basis of V and a basis of W, a basis of V tensor W is in bijection with ordered pairs of basis elements from here. And that certainly fits with this picture here. So even if your vector space, I don't get it from a permutation representation, it still has a basis. Okay. And so in the same way that the obvious basis here of this set is the Cartesian product from the basis we got from each of the vector spaces, you can still do something like that with tensor product. Okay. Oops. Let's see, there's something. Oh yeah, so the square tensor is sort of when I'm gluing together two different vector spaces that come from two different actions. So when I have a setup like, if I have a setup that I have a CG module, V, and let's say a CK module W, then the module that I get, that the new algebra that CG tensor CK acts on, instead of just writing round V tensor W, I tend to like to write V square tensor W to denote it is the tensor product, but the action comes from two separate pieces, and this kind of box times is kind of denoting it's coming from the outside. So I don't know, I just learned that notation as a grad student. And that's the notation I like to use because there's so many tensor products floating around that there's something called internal tensor product versus external tensor product for what the action is. So the fact that the action is coming from two different pieces, I tend to like to put that box around it to denote that. And so it's very similar to like in the symmetric group when we put these diagrams side by side, that like for me, that kind of side by side gluing together new pieces, I would tend to put a box times. But let's see, circle tensor. Yeah, so circle tensor, you could use it for when a group acts. Yeah, so you have in the case where, let's see, where should I put this here? So in the case, so you know that G includes into G cross G diagonally, right? So we might put a delta here for the diagonal inclusion. And in this way, if V and W are both representations of G, right? So this might act on, let me write it this way. Whoops. So I might say G cross G acts on V tensor W, but just the G via this map, this diagonal map delta, acts on just V tensor W. So G cross G acts on square tensor VW, but G just acts on V round tensor W. And that's my notation. You might not see other people using that notation. Let's see. All right. And then also there was a raised hand. Did that get resolved? Okay, well, speak up if not. Okay. Yeah, all right. So tensor product of vector spaces, you can just really think of it as the vector space on sort of ordered pairs of basis elements that you take, one from each set, or you write them as little simple tensors. And likewise, you could take tensor products of algebras, where as an underlying vector space, it is the tensor product of the spaces, and then you extend a multiplication on it, sort of almost in an ordered pair kind of way. And the underlying example that, again, if your algebras happen to be group algebras, what is the algebra you get that's, say, CG tensor CK? It really is isomorphic to C of G cross K. And if you just follow your nose on that, that'll help you get a feel for what happens when you take a tensor product of algebras and what does the multiplication look like. Okay. And I'm happy to talk more about that or do more about that in the exercises. And let me check, I go all the way to the hour.
There hasn't been more questions until now, so I would suggest that you can continue.
All right. So, So tensor product. So another thing that we can do with tensor product, we can use it to make the functor of induction. And so I'll explain in a minute for those of you who don't know it. So here I took the group algebra and I tensor it with the vector space, but then I have this little decoration of another group algebra sitting underneath it. And whatever we mean by this tensor product, it helps it builds up this functor. If H is a subgroup of G, I'm inducing from H to G a representation W of H. And one way to describe that, so you can look, I guess, in Sagan, and you can do it just knowing about groups, but really this is a good way to think about induction in vector space land. Okay, and so what's going on with induction? Oops, let me just shrink that down a little bit. So restriction took us from a representation of G to a representation of the subgroups by restricting the action, right? And you might say, well, what if I want to go backwards? What if I start with a representation W of H and I want to build a representation of G out of it? This is the way to do it, or this is a way to do it. Okay, this is induction. It goes in the other direction. And as we'll possibly see later, in the same way that sigma and sigma inverse were adjoint operators with respect to dot product, it turns out that restriction and induction are adjoint functors, or at least adjoint on one side of each other. Okay. All right, so how do I think, especially if I'm new to tensor products, how do I think of this tensor product, or what do I mean by it? What does this decoration mean? Well, you can think to yourself, first take the vector space generated by elements of the form, like simple tensors, little g tensor, little w, and generated by as a vector space. So I get to take sums, linear combinations of these, okay? And if I did that, I would at the moment get a vector space of dimension the size of G times the dimension of W. But I have to take into account this little decoration over here. And so these are some of my relations. So my relations are that if you give me any H and H, oh, sorry, and this is for a G and G, and a vector W and W, right? Oh, I've written it down here, but I'll write it again. If you have the product in the group GH times W, you make that the same thing, whoops, as G tensor HW. So the H gets to top over the tensor. And then what do I mean by HW? Well, I started out with the representation of H, so HW makes sense. Okay, and so this cuts down my dimension considerably. Okay, right, and so how do we know the dimension of a vector space? We find a basis. So if we take into account that these are my relations, and then my other vector space linear combination, etc. relations, yeah, how do I get a basis? How do I get a basis of this? Well, one way to do it, let's say we start with the basis, little w1 through wk of my vector space W. And I need to now take a system of coset representatives for G mod H, and actually left coset representatives. And if I do that, my basis will be of the form, I could take sigma i's, tensor W, let me say WKs, because my Ks and Js sometimes look alike, right? And this is for I between, say, 1 and R, if that's the index of H and G. In other words, how many cosets I have. And then K is going from 1 through, I can't use K. I already used K up there, so we'll use a J. J between K and K is the dimension of W. And so hopefully you can convince yourself that this really is a basis of the induced module. And then this brings us to, when we're talking about the symmetric group, that gives us interest in coset representatives, okay, which we might get into more later. So if we're talking about induced modules, we have a vested interest in understanding coset representatives. Okay, right. And so the dimension of induced module, it grows. It's not just the dimension of W, you get the dimension of W times the index of H and G when you induce up. Okay. And I think, let's see, so we only have 3 minutes left. maybe now is a good place to stop and instead leave this example for the exercises of take the subgroup S2 cross S1 and S3 and induce up the trivial representation and actually write out the matrices for them. Okay, I will stop here.
Let's thank Monica. You can also mute yourself and just clap. It feels more. It's like we're in the same room.